Now we will discuss the Rodrique's formula for Legendre polynomial. So this is the Rodrique's formula for Legendre polynomial. So you have to remember the Rodrique's formula for Legendre polynomial, in which you can substitute the values of n. You will have different polynomials, different Legendre polynomials. Okay. Now we are going to check whether this will work out or not. See here, your Pn of x is a Legendre polynomial, and this is your Rodrique's formula. Okay. Now we are going to prove whether this is Rodrique's formula is correct or not for Legendre polynomial. We are going to prove. Now let y equals x squared minus 1 to the power n. We just keep it as y as x squared minus 1 to the power n. Differentiate this with respect to x. So that will give you n x squared minus 1 to the power n minus 1 2x. Multiply both sides by x squared minus 1 on both sides. We are going to multiply this by x squared minus 1. So because this x squared minus 1 to the power n is here, so we are going to multiply both sides. You will get, see here, x squared minus 1 to the power n minus 1. When you are going to multiply this minus 1 and this one will get cancelled, you will get the original one. So that's the reason that they have multiplied. So you are going to multiply. This is the equation. So dy by dx, this is the original one. You are going to multiply on both sides by x squared minus 1. So x squared minus 1 dy by dx, which is equal to 2nx, yet multiplied by 2, so 2nx x squared minus 1 to the power n minus 1 multiplied by x squared minus 1, that will give me x squared minus 1 to the power n. Okay. Now what is this? This is nothing but your y. This is nothing but your y. So I can substitute, instead of this you can substitute y. So x squared minus 1 dy by dx equal to 2nxy. Now I am going to differentiate n plus 1 times using Leibniz's theorem. Okay, I am going to differentiate. It's somewhat tedious, you understand. So differentiating this equation with the help of Leibniz's theorem, n plus 1 times. Okay, so now x squared minus 1, here it is dn plus 2y divided by dx to the power n plus 2, and you have n plus 1 c1, just reduce by 1, so that will be d to the power n plus 1 y divided by dx n plus 1. Now this term is nothing but you will have to differentiate this term 2x. After differentiating you will have 2. See, it all depends on the polynomial x squared minus 1. You write it as it is first term. Then second one, after differentiating you will have the second term. After differentiating you will have a third term. Only 3 terms will exist on the left hand side. I repeat, you have x squared minus 1. You keep it as it is first term. Then second term you will have to differentiate once. So 2x. After differentiating that will give you 2. See here written 2 here. X squared, differentiating will give you 2x. After differentiating that will give you 2. So we have only 3 terms. Is it okay? But for example, if you are having 3x to the power 3, x cube, answer will be 3x squared first. Then after that 6x, after that 6. Is it okay? So like that. Now 2nxy. You 2n, you pull it out. We are going to differentiate n plus 1 times using Leibniz's theorem. So you will have only 2 terms. Keeping this as constant, you will have to differentiate y n plus 1 times Leibniz's theorem. So keeping x as constant, you will have to differentiate. Okay. When you are going to differentiate, keeping this as constant, you have to differentiate x, that will be 1. So answer is 1. So you have n plus 1 c1 d to the power ny divided by dx to the power n. Okay. Now I have multiplied by 2n on right hand side, and I have written there. Okay. These 3 terms, let it be like this. So you have 3 terms. 3 terms I have written exactly as it is. We have the first term x squared minus 1 first term. The second term I have written as, instead of n plus 1 c1 can be written as 2n plus 1 x, I have written as it is. The third term n into n plus 1 d to the power ny divided by dx to the power n. Right hand side I have just multiplied with 2n here. 2n multiplied by x, 2n multiplied by this term will give me this term. See here, n plus 1 c1 is nothing but n into n plus 1. So you multiply. n plus 1 c1 is nothing but n plus 1. So 2n n plus 1. Now I have combined this term and this term. So you have d to the power n plus 1 and this term and this term. This term and this term. And I have brought this term here. So that will give me 2x. You have n plus 1. I have brought this term here. This will be minus n. Correct? 2x minus n. See here, 2x minus 1. I have brought this term. And this term, I have brought this term to this side. That will give me minus n into n plus 1. 2n n plus 1 minus n into n plus 1 will give me minus n into n plus 1. I have brought this term here. So look at the powers. This is only one power we have. These powers are the same. See here, these powers are the same. Here also we have these powers are the same. You connect all the powers, you will get this equation. So next one, n into minus n will cancel. We have 2x, the same term. Here also we have, I have brought this term. So you have, this is your, there's a mistake here. It must be plus. I repeat, see here, 2n n plus 1, just bring it to this side. So that will give you, no, it's correct only. So that will give me minus 2n n plus 1 plus n into n plus 1 will give me minus. So it's correct only. I repeat, see here, 2n n plus 1, I bring it to right hand side to left hand side. So that will be minus 2n n plus 1. And here you have n into n plus 1 plus. So I have subtracted, I have written as minus sign here. So you have minus n into n plus 1, it's correct. Now I am going to multiply throughout by minus sign. So that will give me 1 minus x squared minus sign. This becomes plus, which is equal to 0. So equation 4. Now substituting, we know already this is phi of x, which is nothing but your Legendre polynomial, phi of x. Either you can go with Pn of x or phi n of x. First kind, second kind, doesn't matter. So d to the power ny by dx to the power n is nothing but your phi of x is given by Legendre polynomial. You substitute here. So that will give me 1 minus x squared d squared pi by dx squared. You have minus 2x d phi by dx plus n into n plus 1 pi. Is it okay? Instead of this, you substitute either Pn of x or Qn of x. Either Pn of x or Qn of x. So this is your Legendre equation, which has a solution phi equals d to the power ny by dx to the power n. Okay. Hence we may relate this solution phi of x with the Legendre polynomial Pn of x. So Pn of x equals c times q of x. So already we have found out phi of x. So Pn of x is nothing but c times phi of x, where c is a constant. So your y is given as x squared minus x squared minus 1 to the power n. So this can be written as x minus 1 to the power n, x plus 1 to the power n. So differentiating both sides n times using Leibniz's theorem, we will have the same result, d to the power ny by dx to the power n, which is equal to, we will have to differentiate n times. So x minus 1 to the power n. Okay, first we are going to keep this as constant, we will have to differentiate this. Plus keeping this as constant, we will have to differentiate this. So n plus n times. So x to the power minus 1 to the power n, d to the power n by dx to the power n, x plus to the power n. Then nc1. So nc1 n x minus 1 to the power n minus 1, we will have to reduce by 1. So d to the power n minus 1, we will have to reduce by 1, dx to the power to the n minus 1, and this term will become x plus 1 to the power n. So similarly, keeping this as constant, we will have to differentiate this. So this becomes exactly like this. So we have nc n minus 1 n times, keeping this as constant, x plus 1 to the power n minus 1. So now we have differentiated d to the power n minus 1 dx to the power n minus 1, x minus 1 to the power 1. The last term will be exactly like this, nc1 ncn x plus 1 to the power n, d to the power n by dx to the power n, x minus 1 to the power n. So we have kept this as constant, we have differentiated this n times. Now just putting x equals 1 here on both sides. So both sides of the equation, put x equal to 1. Almost all the terms will cancel. See here, if you put x equal to 1 here, this term will cancel. This term will exist. This term will cancel. Okay. So it's given as both the sides of the above equation, all the terms on right hand side due to the factor x minus 1, except the last term. So last term will exist. So which is nothing but your and d to the power n, x minus 1 by dx to the power n, which is nothing but your n factorial. And you have left hand side is nothing but d to the power n y divided by x to the power dx to the power n, which is nothing but 2 to the power n n factorial. Now substitute x equal to 1 in equation 6. Equation 6 is nothing but Pn of x equal to c phi of x. You substitute x equal to 1 here. So you will have Pn of 1 which is equal to c phi of x when x equal to 1. What is phi of x? Phi of x is nothing but, already we know phi of x is nothing but this. So which is nothing but d to the power ny divided by dx to the power n when x equal to 1. We have found out the value of this, which is nothing but c, which is nothing but 2 to the power n factorial. So c times. So c equals this term divided by this term. So Pn of 1 divided by 2 to the power n factorial, which is equal to Pn of 1, we know already, we have found out earlier, Pn of 1 is nothing but 1. So 1 divided by 2n factorial. So substitute this value of c in equation 6. So we have found out the value of c now. You substitute. So substitute in equation 6 will give you Pn of x. Your c is nothing but 1 divided by 2 to the power n factorial phi of x. Phi of x is nothing but dn to the power n d to the power n y divided by dx to the power n. So y is nothing but your x squared minus 1 to the power n. So completely we can have this is your Rodrique's formula which we started with. Pn of x equals 1 divided by 2 to the power n factorial d to the power n by dx to the power n x squared minus 1 to the power n. So this is your Rodrique's formula. We started with Rodrique's formula, we ended with Legendre polynomial. So Rodrique's formula satisfies Legendre polynomial. So this is the required Rodrique's formula. The last one, using Rodrique's formula, we are going to prove that simple problem minus 1 to plus 1 p naught of x equal to 2. Okay. Now this is your Rodrique's formula. You substitute n equal to 0 here. So this becomes 1 divided by 2 to the power 0 factorial d to the power 0 divided by dx to the power 0 x squared minus 1 to the power 0. So answer will be, this will become 1, this will become 1, 2 to the power 0 factorial will become 1, this also will become 1. So p naught of x equal to 1. And what is asked? P naught of x equals, what is, we will have to prove as 2. So minus 1 to plus 1 p naught of x dx equal to minus 1 to plus 1. Your p naught of x we have found out now as 1. So 1 dx. So you have to integrate dx, that will give me x with the limits minus 1 to plus 1. You substitute upper limit and lower limit, that will give you 1 minus of minus 1 which is equal to 2. The last problem, prove that the integration minus 1 to plus 1 Pn of x dx equal to 0. Use Rodrique's formula, you substitute n equal to 1. N equal to 1, you will get this. Earlier we substituted n equal to 0. So now you substitute n equal to 1. So you have to differentiate only once. So divided by 1 divided by 2 to the power 1 factorial d to the power 1 divided by dx to the power 1 x squared minus 1 to the power 1. So when you are going to differentiate, that will give you 2x. So 2x only once. 1 divided by 2, 2 will get cancelled, you will have answer as x. So p1 of x is answer as x. Now we will have to integrate. So minus 1 to plus 1 p1 of x dx equal to minus 1 to plus 1. Instead of p1 of x, answer will be x dx. So integrating, that will give you x squared by 2. Substitute the lower limit and upper limit and the lower limit. You will have 1 by 2 minus 1 by 2. Correct? You will have 1 by 2, you pull it out and you substitute the upper limit first. So 1, lower limit here, minus 1 whole square. So that will be minus 1 whole square, that will be plus 1. 1 minus is there already. So that will give you 1 by 2, 1 minus 1, answer is 0. See here, you have x squared by 2. Okay, 1 by 2 you pull it out. So x squared, you substitute the upper limit, answer is 1. 1 minus of minus 1 square. So answer will be 0. So this is what we have proved. Okay. So we have finished Legendre differential equation, Legendre polynomial, orthogonal property of Legendre polynomial, then the generating function of Legendre polynomial. The last one we discussed was Rodrique's formula of Legendre polynomial. So that is the end of Legendre differential equation, Legendre polynomials. Thank you, students. Bye.